Justin Miller, Oxnard College Physics here. What are we gonna do? We're gonna do a little problem involving some sound waves. So we've looked at sound waves. We know that they're longitudinal. We know that they have intensity, a power per unit area that the waves fall across, and we can talk about that in terms of decibel levels or in watts per meter squared. There's a nice little correlation between those two quantities. And then we've also got that for spherical wavefronts, that the further you are away from a source of spherical wavefronts, the less the intensity is, or the less the decibel level is. And ultimately, we want to investigate some of that now by doing a nice little problem. So let us just go ahead and do that. So here's the problem. All right, so we're going to take ourselves a nice little source of spherical wavefronts and say that when we're 12 meters away from it, that the decibel level that we measure at that location is 83 dB. So we've got a source. Spherical wavefronts go out, and we have ourselves that at 12 meters away, 12 meters, that the dB level is equal to 83.0 decibels. All right, so what do we want to know? Well, we want to know some things like, hey, what's the intensity at that location? And how far away from the source would we have to be for the decibel level to be X amount? And what are the displacements of air molecules? Stuff like that, maximum displacements. So let us just go ahead and start this off, shall we? Sure. So, part A. What is the intensity? 12 meters in watts per meter squared. All right, so when we talk about a decibel level, again, this is with respect to the threshold of hearing, I0, and what we want to know is, well, what's the intensity then at 12 meters away, given that that is the decibel level at 12 meters away. So what do we got with this? Well, we've got that in general, we can write the dB level is equal to 10 times the log base 10 of the ratio of the intensity. I'm going to call it I sub 12 meters divided by I sub 0. So that's the intensity at 12 meters away, and that is relative, the decibel level is again relative to the threshold of hearing, I0, which is 1 times 10 to the negative 12 watts per meter squared. So in the end, we want to solve this out for I at 12 meters away. What can we do? Well, we've got this is 83 decibels. And then we can divide that by 10. Note that that then is equal to the log base 10 of the ratio of I sub 12m divided by I sub 0. And then, of course, we want to get rid of the log base 10. So we go 10 to the power of this, which would just be 10 to the power of 8.3. Is equal then to I sub 12m divided by I0. Thus, we've got that I at 12 meters away is equal to I0 times 10 to the power of 8.3. And what do we get out of this? Well, we get ourselves that I sub 12m is going to be equal to, again, I0 is 1 times 10 to the negative 12 watts per meter squared, the threshold of hearing. Let me just compute this out. 12 times 10 to the 8.3. 1.995 times 10 to the negative 4, we'll call it. 1.995 times 10 to the negative 4 watts per meter squared. There we go. We've got the intensity 12 meters away. Fantastic. All right, so what if we ask something like, I want to know what the displacements of the air molecules at that particular position 12 meters away from the source are. What is the maximum displacement? So we'll go ahead and say B. S max at 12 meters from the source is equal to what? That's what we want, the maximum displacement of the air molecules. So how are we going to get that? Well, we go back to intensity itself and how it's correlated with the maximum displacement, how it's correlated with the angular frequency, the speed of sound. So that's some other things that were noted in this problem. We've got the frequency of the sound is 1,000 hertz, so that's the frequency of the source, and we're going to assume that we're in air at 20 degrees Celsius, such that the speed of sound in air can just be 343 meters per second. So we'll take that as a given in a sense, and then kind of go with this. So if we want to know what the maximum displacement is, well, we need to know what the intensity is, and we already know what the intensity is. We've got ourselves that the intensity in general is 1/2 rho omega squared S max squared times V. That's it. What's rho? Rho's the density of air. So we're going to assume that we're at normal atmospheric pressure. We're at 20 degrees Celsius. That's great. So we're just going to use 1.20 kilograms per cubic meter. This is rho sub air. All right, so what do? Go ahead and solve this for S max, right? That seems pretty easy. Multiply both sides by 2, divide by rho omega squared V, and we've got ourselves S max. So we've got S max is going to be equal to the square root of 2I divided by rho omega squared times V. There we go, got this all solved out for S max. And no need to put plus or minus because the maximum displacement is always considered positive. It's just a matter of what's our I, what's our V, what's our rho, and what's omega here. So omega is what you got to be a little bit careful with. V we already know, rho we already know. I depends on where we are, and this is where we are, 12 meters away, so that is our I. So this is what we've got. We've got to reconfigure out our omega here. So omega is the angular frequency. That 1,000 hertz is just the frequency in hertz. So we need the angular frequency or some correlation between the two. And what do we have? We've got that omega in general is equal to 2 pi times f. So we could go ahead and sub that in for omega and then have it written out in terms of 1,000 hertz, or we can figure out what omega is in terms of that. Doesn't really matter, but in the end, we've got S max at 12 meters is going to be equal to the square root of 2 times I at 12 meters, which is 1.995 times 10 to the negative 4, 1.995 times 10 to the negative 4 watts per meter squared, divided by, we've got rho, so we've got 1.2 kilograms per cubic meter multiplied by omega squared. So we're going to just call it 2 pi times f in that quantity squared. 2 pi multiplied by 1,000 hertz. And it's that whole thing squared, so it's 4 pi squared, 1,000 squared. And then we've got V. V is just our 343 meters per second, the speed of sound in air. And that will give us what the maximum displacement of the air molecules are at that particular location. So we go ahead, square root 2 times 1.995 e to the negative 4 divided by the quantity of 0.2 times pi pi squared 1,000 squared times 343. all good. 1.2, 4 pi squared, 1,000 squared, 343. And we get 1.566999, or let's just call it 1.567. 1.567. 1.567 times 10 to the negative 7 meters. That's a maximum displacement. Well, how much is that? That's really small, right? That's a really small displacement. Can you see that? Heck no, you can't. Not with the naked eye anyway. If you actually could see the air molecules, would you see them moving that much? No. So it's pretty small. Pretty small. And that's 83 dB, which isn't really quiet by any means. It's a decent sound that's highly perceivable. Really small displacements. We got really, this could be 0.1567 microns. 0.1567 millionths of a meter. Small. But anyway, that's what we typically have, at least for maximum displacement air molecules for sounds that are well below the threshold of pain, or even just below the threshold of pain. Really small displacements. All right, so we move on to a part C. And part C asks, at what distance away would we have to be for the decibel level of the sound to be 70 dB? How far away do we have to be for it to be 70 dB? Well, at 12 meters, we're 83 dB. So it should stand to reason that we need to be farther than 12 meters, right? So the further away you are, the less intense it is, thus the lower the dB level. So how are we going to go ahead and figure this out? Well, we've got to go back to the aspect of spherical wavefronts and intensity. So what can we do with all of this? Well, there's some other ways of writing out the intensity. Note that we can write the intensity as being equal to the average power divided by the area that's being considered, or we just divide it by 4 pi r squared if we're talking about spherical wavefronts. 4 pi r squared, where r is your radial distance away from the source. So the average power, again, is something that is inherent with respect to the source. It doesn't matter how far away you are, the average power is the average power everywhere. So what matters is that the intensity is what actually changes with respect to position. So given that we have this, we can start figuring out what the distance away is if we knew what the intensity was, and, well, if we knew what the average power is. So first off, let's just go ahead and get the average power. How are we going to get the average power? We just go back and consider what we already started with here and how we compute the average power itself. So we had that the intensity at 12 meters away is this, right? Well, what if we went ahead and said at 12 meters we've got I sub 12 meters, that has to be equal to the average power divided by 4 pi times 12 meters quantity squared. That has to be how things work out. These two correlate. This is a constant value for a particular system, if there's no fluctuations occurring. Anyways, that gives us the average power then. So we can write ourselves that the average power is then just equal to I sub 12m times 4 pi times 12 meters quantity squared. In order to get, this is in watts per meter squared, times meters squared just gives us watts, and that's what we've got. That's what we want, some watts. So there's the average power there. And then we want to know, well, what distance away is the decibel level 70 dB? Well, do you see decibel levels in here anywhere? And the answer is, well, not explicitly. It's built within this, right? The decibel levels are connected back with the intensity itself. So we've also got this I to deal with. So at some distance away, we have that the decibel level, and I'm just going to call it dB level, at some distance away, x has to be equal to 10 times the log base 10 of I sub x divided by I0. So we know what the decibel level is that we want. We want it to be 70 dB, and with that we can figure out then what the intensity is regarding that decibel level. And once we know what the intensity is, that's there, we can solve it for R, which is the radial distance away that we have to be from the source that has the average power given by that, which correlates back to what we've already solved here. So kind of a few things that need to be put together there, right? So that's kind of how this is all interwoven here. I'm going to kind of unravel it, so to say. So let's just go ahead and do this. Let's do this one part at a time here. Let's get ourselves I sub x. So what's I sub x going to be? Well, we've got that this is, again, 70 dB is equal to 10 times the log base 10 of I sub x divided by I sub 0. And with this, we can go ahead and get ourselves the I sub x is equal to I sub 0 times 10 to the 7th power. Divide by 10, raise everything 10 to the power of, and that's what we get. So there's our I sub x. If we wanted to, we could quantify it, that would be fine. But really, what do we need to do? We need to solve this for R. So we could rearrange this expression here for R and write ourselves that R is going to be equal to the square root of average power divided by 4 pi I. Square root of P sub average divided by 4 pi times I. All right, so what do we do with this? Well, here's the average power right here. We could quantify it, get a number, but that's how we're getting it, right? By what we already knew at the 12-meter mark. Fantastic. What about I? Well, I is I sub x. That's some distance away that we're trying to actually figure out. So I'm calling it R here just because that's what's in the expression, but this is the distance away at which the intensity is this. So I'll say we could write this out as R is equal to the square root of I at 12 meters times 4 pi times the 12 meters quantity squared. All right, and then that is going to be divided by 4 pi times I0 times 10 to the 7th power. See some stuff that cancels out there? Heck yeah, you do. Heck yeah, you do. Well, we've got ourselves the 4 pi's cancel out. That kind of cleans things up a little bit, right? So we can write this as R is equal to the square root of I at 12 meters times 12 meters quantity squared divided by I0 times 10 to the 7th. And that's easily computed. And what do we get? Well, we've got the I0, I sub 12 was 1.995 times 10 to the negative 4. So we'll take the square root. 1.995 e to the negative 4 times 144 divided by the quantity of 1 e to the negative 12 times 10 to the 7th. 53.598. There you go. When you're at 12 meters, the decibel level is 83 dB. When you go 53.598 meters away from the source, now the decibel level's 70 dB. So it seems like you got to move pretty far for the decibel level just to drop down 13 dB. But that's actually pretty significant in terms of intensities, right? So that's just how we roll out with this, right? We can figure out the dB level really at any location, or the location that we need to be at for any dB level, given what we know here. All right, so I think that was pretty good. I went through most of the stuff. I think if there's anything else that we should do with this, or could do with this. Little things you got to be aware of. What if we change the temperature, right? The speed of sound in the air changes. But yeah, I think that's pretty good. Alrighty, sounds fantastic. Sounds fantastic, get it? Anyways, have a good one. Until next, more to come. More to come. Oof. Be well.